Assalamualaikum. Hi guys. In the previous video, I introduced to you 4 characteristics to allocate the position of electron in orbital. We are going to use quantum numbers. So quantum numbers, there are 4 of it that you can see from this slide. I'm going to explain to you one by one. Let's go to the principal quantum number n. Principal quantum number determines the energy or energy level or shell and also the size of orbitals. So each quantum number, they got their own purpose. Next, the principal quantum number can only have positive integral values, which n starts from 1, 2, 3 and so on until infinity. It cannot be in negative value. For example, if I have n equals to 1, this is what I have as my first energy level. I will put my shell as k, unknown k. So if you have n equals to 1 is the smallest energy level, so the orbital size is the smallest compared to orbital size for 4th energy level. So as you see here, from n equals to 1 until 4, the energy increases. This is because the shell or the orbit is further from the nucleus. So what we can conclude here, the larger the n value, it means that the larger the size of atom. Hence, larger the distance between electron and nucleus. Next, we are going to continue for angular momentum quantum number, L. So in this part, the purpose for L is to determine the shape of atomic orbitals and the types of orbital. So the alternative name for angular momentum quantum number, we have another 3: azimuthal quantum number, subsidiary quantum number, and orbital quantum number. They all bring the same name as angular momentum quantum number. So the value for L is depending on the value for n, the one that we talked about just now, principal quantum number. So you have to know how to determine the value for n first, and later on you can determine the value for L. For example, if I have for a given value for n, you have to make sure that your L must start with L less than n. So for example, I have n equals to 3, so your L value must be less than n. It can be starts from 0, 1 and 2. So only these 3 numbers are less than 3. So that's how you want to determine L value. Next, you have to understand as well, L value also can determine the types of orbital. So of course, the types of orbital can exist in the different subshells in the main energy levels. For example, I want to describe 3 things here based on angular momentum quantum number. Based on the numerical value of L, I can also determine the symbol for orbital and the shape for the orbital. So let's go to the L value. If I have L value, which is the lowest one, is 0, so the symbol of orbital will be S, and the shape is spherical. Next, when L equals to 1, the symbol is P, and the shape is dumbbell. When L equals to 2, the symbol is D, and the shape is cloverleaf. When L equals to 3, the symbol is F, and the shape is irregular. So these all you have to memorize, and the value for L equals to 0 is fixed for the symbol of S orbital with its respective shape. So how this orbital shape can be formed here, it depends on the naked eye to observe how the electron cloud surrounds the nucleus of an atom. So that's why for S orbital, we can see the electron cloud make up the shape for spherical. That's why we have s orbital when L equals to 0, the shape is spherical. Next, let's try one example. What I have here is my table. I want to determine based on n value. So n value is principal quantum number where I can determine my orbit or my shell for that atom. Next one, we have a new term here, subshell. Subshell is the same thing to refer to the angular momentum quantum number, L. And the next part, we have type of subshell. This is the type of orbital, but you have to be specific based on which shell. So let's try one example. When I have n value is the second energy level, n equals to 2, so I can have the L value which is less than n. So my L value can be 0 and 1. So if I want to write my subshell is depending on the value for L. When L equals to 0, the orbital symbol is S. And right now I got my shell is 2. So the type of subshell will be 2s. And next, I have L equals to 1. The symbol is P. But we talk about the same energy level, so the type of subshell will be 2p. For example, I give you n equals to 4. So same goes, L must be less than n. So you have 4 different values for L. And if I want to describe based on the type of subshell, I know all of these value for L, there is a specific symbol for the orbital. For 0, it will be 4s. For 1, it will be 4p. When L equals to 2, it will be 4d. And when L equals to 3, it will be 4f. So it is very important for you to memorize S, P, D, F, because it brings the value for L equals to 0, 1, 2, 3. Let's continue with magnetic quantum number. Magnetic quantum number with the symbol M, it can determine the orientation of orbital in space and the maximum number of orbitals for a particular value for L. So now you have to understand the next quantum number here, it will depend on the previous one. So now for magnetic quantum number, M depends on the value for L. So you have to know how to determine the value for M, where usually M can be for negative L until positive L. So this is to show the orientation of orbital. For example, I have L equals to 2. I know that this is d orbital. So when d orbital, we want to find out the value for magnetic quantum number M. And we know it depends on the range for L from negative L until positive L. So the value for M can be starting from negative 2, because L equals to 2, we start with negative 2 until positive 2. So you have to list down all the values between them. This is how you use the range of scale 0, and then to the right we have 1, 2, 3, and to the left we have negative 1, negative 2, negative 3. Next, I want to determine these 5 numbers is correct or wrong. I can use this formula to determine the number of permitted values of M. We have 2L plus 1. So this number, I can determine whether we have the correct number of orientations or not. So I'm going to put my values 2 here for L in this case. So I will have 5. So 5 here is showing that 5 orientations of d orbitals. So this is where you have first orientation is M equals to negative 2. Second one is M equals to negative 1, and so on. So it means that this value for M is correct because I have 5 of them. Let's try one example when n equals to 1. So we know that n is the principal quantum number. So I'm going to determine L equals to 0 because L must be less than n. And then when L equals to 0, this indicates the subshell of orbital S. And the next part, I'm going to continue with magnetic quantum number, where my magnetic quantum number equals to 0 as well because L is 0. This is what I have to indicate that only one orientation because only one value for M, and the subshell is 1s. This is because you have n is 1 and you have the shape of orbital is s based on L value. Let's try one more example when n equals to 3. So I know that I can have 3 different values L, which could be 0, 1, and 2. But for example, I want to take L equals to 2 only. So I can know that L equals to 2 indicates subshell or orbital D. This is because the value L equals to 2. And next, I want to determine how about my magnetic quantum number. I will put the range for negative L until positive L. So you will have these values as 5 orientations of my subshell 3D. This is because you have n value is 3 and D is for the shape of L equals to 2. Next, we go for the last quantum numbers of electrons, which is electron spin quantum number. The symbol is S. So, based on this part, S can determine the direction of spinning motion for an electron at its own axis. And the spinning direction can be clockwise or anti-clockwise. It depends on which one that you want to use. And we are going to indicate the direction clockwise and anti-clockwise by using the number positive half for clockwise or negative half for anti-clockwise. So let's go to the final example where if I want to determine the relationship between N, L, and M, what I have here, for example, I have N equals to 1, so the value for L should be 0. The subshell is 1s, and I can have my M value stay as 0 because L is 0. So how many orbitals in my subshell? I got 1 only. So this will be my answer. Next, if I have N equals to 2, I can have L value 0 and 1. So my subshell will be 2s and 2p. How about the M value? I'm going to determine one by one. So M value for 2s will be 0. For 2p, it will be negative 1, 0, and positive 1. So if you take a look here, for 2s, you have one orientation only. So that's why one orbital in this subshell. But for 2p, you have 3 orientations. So it means that you have 3 different orbitals in this same subshell. Let's go when n equals to 3. So you can have the value for L 0, 1, and 2. So your subshell can be 3s, 3p, and 3d. And next, let's continue with 3s. The M value should be 0. For 3p, 3 values. And for 3d, we have 5 values. So if I want to determine how many number of orbitals in subshell 3s, I have 1 because M value only 1. If I want to determine in subshell 3p, I have 3 number of orbitals. And last but not least, I have 5 for subshell 3d. So this is how you determine, based on this example, the relationship between principal quantum number N, angular momentum quantum number L, then magnetic quantum number M. I'm going to bring this all information together to relate with the last quantum number, electron spin quantum number S. So this is where we are going to continue. With this one, we have two different directions for electron spin, and we know that the number of orbital is 1. So the number of electrons can be 2 because we have two different spin here. First electron for clockwise direction and the second one is for the anti-clockwise direction. Next, if I got here from the previous, the same spin is going to be for each of the subshell. And you have one orientation only for 2s, so the number of orbital is 1, but you have 3 for 2p, so it will be 3. Now, if I want to determine how many number of electrons, I'm going to use 2 of these times with one orientation, so you have 2. And then here, you got 3 of these. So, in one orbital, the maximum number of electrons is 2 because different spin, positive half and negative half. So, I'm going to multiply by 2, we got 6 here. So, 6 plus 2, it will be 8. Next, I have the same things goes for the electron spin. And now I have 1 for 3s, 3 for 3p, and 5 for 3d. This is because of the orientation values. And next, if I want to determine how many number of electrons, please remember one orbital can hold maximum 2 electrons. So from here you got 1 orbital, 2 electrons, 3 orbitals, 6 electrons, and 5 orbitals, 10 electrons. So if I want to add up all of them, it will be 18 number of electrons in third shell. Next, we have 4. We can have 0, 1, 2, 3 for L value, 4s, 4p, 4d, and 4f based on its shape. And we have 0 for 4s, 3 values for 4p, 5 values for 4d, and we have 7 values for 4f. And now the electron spin will be plus minus half for each orientation. And now we are going to determine number of orbitals. We have 1 value here, 1 for 4s, 3 values, 3 orbitals, 5 values, 5 orbitals, and we got 7 values, 7 orbitals. So in this case, one orbital can hold maximum 2 electrons. So each of them, for one orbital, 2, here is 6, here is 10, and here is 14. When you add up everything, you will have 32 electrons in the fourth shell or fourth energy level. So this is how you determine based on principal quantum number, angular momentum quantum number, magnetic quantum number, and electron spin quantum number. All of them are related to one another. So, I hope you understood about this video, how to determine the value for each quantum numbers. So that's it for now. I'll see you in the next one. Bye!